I was at Meta for about 5.5 years. I left about 2 months ago. But yeah, today I will talk about retrieval at the frontier, specifically what it looks like in the era of, in the era of long context LLMs and multimodal LLMs. Okay, the general agenda today is there's two streams that I promise will intersect at the very end. The first stream is talking about the foundations of retrieval, why retrieval is necessary, and then what the future of retrieval is now that we're getting very long context language models. And then in the second half, I'll talk about Omni models. These are essentially natively multimodal models. This is what our team developed for about 2 years at Meta, and I think the best well-known example of a Omni model is GPT-4o. So you'll learn a little bit about how GPT-4o was developed as well, at least our best guess to how it was developed. Okay, let's start by maybe centralizing the conversation and talking about the core foundations of retrieval. I think the best way to... Perfect. Okay. The best way to think about this is to think of retrieval as just prepending your key value cache in your transformer. And the reason that I like to talk about it this way rather than prefixing a prompt is because there's a huge surface area of different ways that you can do retrieval, from the KV cache level to the prompt level to some weird mixtures in between. But in general, what we mean by RAG is that we have a separate retrieval model that is able to just prefix the KV cache for some user prompt. And so what is retrieval? Why do we need it? From very fundamental first principles. The very first thing that I will state is that retrieval, in the way that we formulated it, fundamentally does not augment capabilities. So you're not going to get your step-level reasoning improvements by including retrieval in your pipeline. You're not going to be able to go from GPT-4 to O1 by prepending any type of prompt. So retrieval is fundamentally useful in two different places. The first is when you want to augment some semantic knowledge, whether that's some tail entity knowledge that is probably very unlikely to exist on the web, or you're a company that has some private semantic knowledge that you want to kind of prompt the model with. And the second place that retrieval helps is when you want to refine a task understanding. So if you have a very complex prompt, you want to be able to demonstrate rather than describe what exactly you want to do. I think in the research role, we call this in-context learning. And this is one of the other fundamental reasons why retrieval is necessary. Specifically, when we talk about why we need separate retrievals rather than using very long context, there's kind of a unified answer here, and the unified answer is that attention is actually relatively expensive, and I actually will not treat this as a first principle. I'll challenge this, but the way that this pipeline looks like is that you have a very high recall system because LLMs are quite expensive, and this very high recall system is your retriever. So if you've ever worked on traditional search systems, this is what's traditionally called like your L0 step. And your LLMs are a very, very high precision engine that is very expensive to run, and context length is kind of how your compute grows with your high precision system. So for retrieval specifically, it's a very fundamental question of how do we best use our context window. So like I mentioned before, one of the core reasons to use retrieval is you want to bring custom knowledge into context. Essentially, this reduces your tail knowledge misses. There's no expectation that our language models are going to be able to memorize every single fact, nor do we want this, just from a large-scale pre-training perspective. So by prepending some additional semantic knowledge, you can reduce kind of the heaviness of LLMs needed for your specific task. The other thing is it's low cost. You likely don't want to fine-tune a model for your specific private semantic knowledge database. It's kind of non-trivial. Data mixes are hard. You don't want to have a company that's running thousands of fine-tuned models while the underlying capabilities of the models are exactly the same. And by the way, this was the case, right? So before there was ChatGPT, we were all fine-tuning BERT or Roberta or BART on a million different tasks, and we would actually productionize thousands thousands of these models, and this logistically is just a big nightmare. The other thing that is notable is interpretability. So proper prompting will allow your model to cite your in-context knowledge. You kind of see this with ChatGPT, but I think the best example here is Perplexity, which is able to just very directly reference specific documents that it's looking at. And this is all, of course, done through a proper RAG setup. And the secondary thing that I mentioned, which is augmenting task descriptions, this in-context learning. Sometimes your prompts are very, very complicated, and it's very hard to get the model to reason about what you want it to reason about. So you can give examples of some tasks to clarify the underlying semantics of the tasks. And this was the foundational breakthrough that GPT-3 had, right? Which was that you can add a prompt, but you can actually just give examples of your concrete tasks, and the models are able to learn it dynamically. And this is one of the other core reasons why retrieval works in complex settings when you don't just want to inject some facts into it. Now I'm going to pivot a little bit and talk about this concept that I think has been proliferated probably because of the very early days of transformers, which is that attention is expensive. So the question that I want to ask is, how cheap can attention actually get? And kind of the follow-up after that is, do we really need separate retrievers if we can eventually just put everything into context? So the key thing that I want to say from training these foundation models for a very long time is that attention is actually not computationally expensive. So I think we constantly hear that, asymptotically attention is kind of O(n) squared, where n is your context length. But functionally, attention is actually one of the cheapest operations as you scale parameters. So this is a little graph I created from some very standard model sizes that were introduced in GPT-3 and then also subsequently used in the Llama series. And you can kind of see the green line is the cost of all your feed-forward operations, which is actually very great because these are matrix multiplications and GPUs are very, very good at doing this. And the red line is essentially the cost of your attention. And so you see, as we scale up the size of the model, we're looking at like sub 20% cost being in the attention. So attention as an operator is actually kind of fundamentally quite cheap. And so the real cost is in actually the memory of being able to represent the embeddings over which you do attention. What I want to do is cover a couple of the recent very state-of-the-art techniques in order to reduce the cost of attention, and you'll kind of get to see how Gemini gets to, let's say, 10 million context length without really changing anything in the transformer. Probably the most well-known example of pruning attention is this concept of grouped query or multi-query attention versus the very traditional multi-head attention. So the key realization was, and this realization was maybe 3 or 4 years ago, is that you actually don't need to represent your sequence as multiple keys and values for every self-attention head. So really what you can just do is reuse your key and value heads within a single multi-head attention block. And if you do this, you actually don't need to store the number of heads of embeddings for all of your keys and values. And so this was introduced quite early, maybe in 2021 from Google, and eventually it made its way into very popular trainings. And I think most of the big models that you use today all use either grouped query attention or multi-query attention. So if you folks use Llama, if you use any of the Mistral models, if you use Chameleon, these are all using group query attention that are able to get us anywhere between 4 to 8 reduction in memory cost. So this is pretty good, but we can keep going. The next big thing that the labs were doing but wasn't published until relatively recently is this concept of key value sharing. So this is asking a very fundamental question, which is, as you progress through your transformer layers, do you actually need to recompute new keys and values every single time? And it turns out the realization is no, you actually don't. And what you can do is just reuse your key value embeddings across layers. And so this is what Character AI does. I'm not sharing secret knowledge. This was in their blog post. But you can furthermore reduce cost by about 2 or 3 times. And then you can keep going. You can start thinking about, well, do I need to do full attention over my sequence every single layer? And the truth is you probably don't. The majority of what you want is within, let's say, 1,000, 2,000, 8,000 tokens before you. So we only really need to do full attention every once in a while. So this is what we call local attention, which is looking maybe 8K tokens behind you. And then you have full attention, which is looking over your whole, let's say, 1 million or 10 million sequence. And just by alternating this local and global attention, you can further get 6 to 8x reduction in memory cost. The reason I'm saying this is Noam's architecture, this is Noam Shazir, who developed all of these techniques at Google, and he was the CEO of Character, and I guess he's back to Google now. And kind of the last point that I will touch upon, just kind of on the theme of, well, how much attention do we actually need? There's a question of, do we actually need full rank attention? The idea being is, can we actually compress the keys and values using some very basic compression scheme? And it turns out that you can, and this technique is used very, very heavily by Chinese labs that are putting out LLMs. And it turns out that, yeah, you can actually run some basic like rank compression and get an additional 6 to 8 reduction in memory. Again, without any significant performance gap. And so these are the core basic ways that you can reduce attention cost in modern transformers. And these are all public. And of course, there's ones that I'm not sharing, and there's ones that I bet OpenAI is not sharing either, which will allow you to get much further. But in a very basic sense, just from like what's publicly available, we can actually get anywhere between a 200x to 1500x reduction in memory cost. So essentially, this means we can kind of trivially scale up to about on the order of 10 million context length. Which if you folks follow the very long context models, you'll see that we're kind of around there. So I think the Gemini Flash models can get up to 10 million context lengths. So this is very, very likely how they do it. And so very interesting things start to happen if you can actually very effectively use your context length. The one that I will talk about, and this is a personal hypothesis that we will actually get here with GPT-5, it's that if you have very effective context length, you can essentially completely deprecate fine-tuning. At some point, just doing in-context learning when you prefix your examples will allow you to get better results than you fine-tuning your own model. And of course, this is not true yet, but personally, I believe it will be true with GPT-5. And the moment that this happens, fine-tuning as a mechanism of customizing models, I think will disappear. Probably not in the open source, but for big companies like Anthropic and OpenAI, it likely will. So if you take all this into account, there's a couple of pretty severe implications for RAG. The first one is that if you have a very effective use of context link, your custom-trained retrieval-aware language models like the ones that Cohere has are essentially commoditized. I no longer need to fine-tune a model to understand retrieval. I can just use an off-the-shelf model. The role of the retriever ends up being a little bit more weakened, which I will actually argue is a good thing. Essentially, being very clever about what parts of your key value cache you store, plus very long attention, is essentially what the retriever does. Yet, the role of the retriever maintains the same. So the goal is still to maximally use context length. And the goal here is that you can continue using separate retrievers to maintain cost effectiveness. And a very easy way to look at this is just to look at the Gemini Pro APIs. I think these have gone in cheaper since I screenshotted this, but it's order of about the same. You can see that still having separate retrieval models that allow you to cut your context length by about an order of magnitude will save you non-trivial amount of money. And the good thing of having models that are very good at interpreting very long context lengths is you no longer need to deal with any of the complexities that we used to have to deal with retrievers. So we no longer need to think about like, oh, well, what's the proper way to do chunking? It probably doesn't matter if you think the document is important, just drop the whole document in there. You no longer specifically have to fine-tune retrieval models. You don't need to do things that many people have done around like hierarchical document summarization. Again, you have a very long context length, just drop it on in. And same thing with carefully filtering data. This L0 step of having a very high recall model, while still needed, it doesn't need to maintain the same level of precision that you need now. Essentially, you can drop a lot more documents into these models, and your LLM will still do very, very well. So for a while, within the text-only space, it will still be cost-effective to run retrieval models. But likely in the long term, as compute keeps getting cheaper, as inference keeps getting cheaper, there will be a phase shift in the way that we think about retrieval in general. And I'll talk about this a little bit at the end of the presentation. So from here, I want to pivot a little bit to our work, and I promise that at the end it will all intersect. So specifically, I want to talk about what we called early fusion models. I think internally within Meta, what GPT-4o coined as Omni models. And so I will specifically be talking about our work here. And again, I want to start off by thinking about first principles when it comes to training very, very large models. The key realization that we had about maybe a year and a half ago to 2 years ago when we started working on this was that in general, we're running out of text. So if you remove synthetic data generation, you're probably looking at, there's maybe 30 trillion very high quality multilingual tokens on all of the web. If I scrape all of the web, I'll probably be able to extract about 30 trillion tokens. For some context, Llama was trained with 15 trillion tokens. So essentially with H100s at scale, we're close to surpassing all the text-only tokens that exist in the whole world on the web. The good news is that we can find ways to continue the scaling patterns that we've seen with language models. The moment that you touch multimodal, if you start looking at gathering very high quality images and text, you're actually starting to look at about 200 trillion tokens, which is still kind of in the ballpark of what's possible to train in the next year or so. But the moment that you start getting into much denser modalities, such as like very high quality video, you're starting to look at about a quadrillion tokens, which essentially means we have maybe another 5 years worth of ramp to continue scaling up these models. And so the very fundamental question that we asked is that, we have these very core recipes for training on text that scale very, very well, but we actually have no idea on how to train multimodal models. And this is essentially what our team focused on. And 2 years ago, we had this research hypothesis, and the research hypothesis was that these early fusion, and we'll get into what that means very soon, but these early fusion multimodal models and their training recipes will be the next step level change that we see in language model performance. So this was a hypothesis that we had 2 years ago, and we've been working on this since. The core bet that we took was this concept of early fusion. This is kind of a fancy term to say that you start training your text and image modalities from scratch. You see a lot of multimodal models right now that are done in a very late fusion way, where essentially you will take a Llama model or you will take a Mistral model, and then you will kind of conjoin it with some vision models and train a little bit and get something working. The ceiling essentially for late fusion models we figured out was very low. So our bet was we essentially wanted to have a consolidated approach to training multimodal models. So we wanted to train everything from scratch at once. And so our approach was, well, look, we know how to train text-only language models. It's probably way too high risk to try anything that's very, very fundamentally different, especially when you're operating at, thousands of A100s or H100s. So we said, okay, let's continue on this language model trend, and let's just convert images to their own language. So essentially, let's take an image and let's convert it to, let's say, 1,000 tokens, some 1,000 discrete tokens, which is essentially a language for images. And if you're able to discretize everything, then you can essentially continue to train in the same way that you always trained, which is you have an autoregressive language model. It predicts a token one at a time. And the core idea that we had is that, look, we're tokens in and tokens out. You can have any tokens. You can have image tokens. You can have audio tokens. You can have video tokens. And same on the output, which means that you'll be able to jointly do image generation, in theory, video generation, which we never did, audio generation, which folks like Google have done, and text generation all at once. And furthermore, our idea was like, look, we don't just want to model text or specifically text to image. We want to model like full documents from scratch. So like full Wikipedia documents, full PowerPoint presentations. We don't want to enforce any type of arbitrary, we don't want to enforce a specific alignment between the text and images. We should just take them as they come. And this will essentially allow us to continue scaling for about 2 more years. And this figure here is exactly what we do. You essentially have text, which is tokenized in this very traditional way. And images are tokenized with an image tokenizer, which is outside the scope of this presentation, but just believe me, it takes an image and then outputs 1,000 tokens that represent this image. And we just model it autoregressively left to right. And we slowly started working on this, and throughout, I think, the last 2 years, we essentially saw that if you do things properly, these things actually scale just about as well as text-only language models. So the scaling laws here are actually kind of on our side. And furthermore, they were scaling better than modality-specific models in specific domains. So for example, we were able to scale better than Stable Diffusion, which were diffusion models. We were able to scale better than things like Party, which came from Google, which were like encoder-decoder models. So we thought that we actually found something that is pretty fundamental, that this autoregressive language modeling objective is probably the best objective that we have. And by converting everything to a language that we model, we were actually going to get somewhere very cool. And furthermore, we realized that because we're modeling everything at a token level, we can essentially do any arbitrary task. So you can prompt images for any task. So if you want to edit an image, you can just prompt the image by saying, edit this image following some text instruction. Or here's a rough sketch that I have of an image, make a high quality sketch. Or you can ask it to give you like bounding boxes around some entity just by asking what coordinates of the bounding box. And so what we realized is that this Omni approach, or this early fusion approach, was actually very, very flexible and very scalable, which to us all of a sudden started to get us excited, because we thought that we could really scale this up and get some very, very fundamental capabilities that other folks did not have before. And this is where Chameleon kind of got born. So we started this project, I think September of 2023, and we wanted to train the world's first Omni model, and we wanted to open source it. So our team of about 40 people, we collected the largest scale mixed modal training data set that was kind of ever curated. I'm sure OpenAI has something that's larger, but at least in the open source. So this consisted of about 9 trillion tokens from Llama 2, from Code Llama, from arbitrary web pages, from text to image data sets, from videos. And we essentially trained a couple of model sizes on about 3K GPUs, 2 months each. And then we had our own separate pipelines for doing very high quality supervised fine tuning so that we can actually get something that is usable. And what we saw very quickly was that our relatively small models, our 30B models, were actually competing with Gemini Pro. Like we were actually winning out on human evaluations when looking against Gemini Pro, which I don't think this is too much of a secret now, but Gemini Pro at that time was about a 60 billion parameter model. So we were able to essentially beat out a model that's 2 times larger, that was probably trained for about 5 times longer, just by having the proper recipes and unlocking this new capability of scale from the perspective of Omni models. And so this is an example. I think on the left is the GPT-4v with DALL-E example. On the right is what Chameleon was able to do. Essentially, we were able to generate like full Wikipedia pages with arbitrary images, all generated from a single model that had a very deep understanding of alignment between text and images. Yes. At that time, we had some concurrent amount of work because we started seeing some weaknesses of these Omni models. The biggest weakness was that, look, there's a ton of there's a ton of tail entities within the image domain. There's a lot of different landmarks. There's millions of different landmarks. And it's very unlikely that our models will be able to memorize them all. So we turn to RAG as a solution. And the great thing with Omni models is because it still operates like a token-level language model, you apply RAG in the same way that you apply RAG to text-only language models. And this is exactly what we did. We essentially were able to use a separate retriever, I think at that time it was Clip, to essentially pull up some documents that were multimodal in nature for some specific prompt that we wanted to operate over. And it turns out that actually works very, very well. So we were able to generate much more accurate images than Stable Diffusion was at that time, which was the state of the art about a year and a half ago. Just by being able to prompt with some specific tail entities. And the other thing that we noticed is that we were actually able to mix compositional knowledge. So you were able to give a couple of different images and then ask it to mix it together. And the model will actually be able to do this quite well. And if you work with diffusion models before, you know that this is actually very, very tough to get done in a proper way. They're very directly just a pure text-to-image model. So we started seeing that, in general, the classical approaches that were able to run on text were very quickly moving to Omni models. So now what I want to talk about is what we term the token economics of these modern models, like GPT-4o, like Chameleon. And I want to start off by making a relatively strong statement, but I think this will likely be true. I think about 100 million contexts like this probably possible within the next year. If we just need maybe 2 more techniques that give us, 10x improvements in memory, and we will be able to get there, or 5x improvements in memory. And so if you think about this in the text world, 100 million context length is about 1,000 books. It's 50% of the Linux code base. It's about 5% of Wikipedia, and it's a very small percentage of the full web. But 1,000 books of text is non-trivial, right? For most, private companies, 1,000 books of your private data would seem to be enough. And at that point, you would no longer need to do any type of a separate retrieval. You could put everything into a single prompt, cache the prompt, and it should work. But this is where things start getting interesting. If you start thinking about having private semantic knowledge that is multimodal in nature, you start seeing that this drops quite significantly. So we go from 5% of Wikipedia to 0.05%, and all of a sudden things start getting interesting where you actually do have to use RAG again, because although context length went up, the amount of density of information that we want to put in goes up as well. And then if you really, really want to get multimodal and you start thinking about world models such as video models, a single 2-hour-long video at 16 frames per second will give you about 100 million tokens. So now we're operating in a space where we're back at the beginning, which is that if you have a very fundamental multimodal problem that needs to be solved, you need to go back and operate with RAG. And so I'm going to finish off this talk by giving a prediction of the future of RAG. My guess is that the impact of improving retrieval for text-only models is diminishing quite quickly. I think especially once we get to about 100 million context length, there will be an inflection point where the context length and actually the very effective use of the full context length, you'll be able to match very fine-tuned RAG very, very soon. And this is actually a good thing. That means you don't have to spend cycles building out very, very complex RAG pipelines. You can focus on a much higher level of abstraction. Good news for folks that want to continue building RAG is that Omni models will absolutely continue requiring RAG. Simply, if you go and you look at the GPT-4o pricing, either for the real-time application or even their base application, it's prohibitively expensive to do anything where you're putting in, thousands of images that you want to operate over. And like I said, Omni models that support video understanding is probably going to be the next frontier of RAG. If I want to do video search over, 100,000 hours of video, there's no way in the next decade, my guess, that will be able to support in a very cost-effective way placing all these videos into a single prompt. I think that's it for me. I think there's 1 minute left, but yeah, thank you for your attention.